Tonight, we are not traveling outward toward distant galaxies or drifting through the cold rivers of interstellar space. Instead, we are descending inward, beneath atoms, beneath light, beneath the familiar shape of matter itself, toward a hidden layer of reality that may exist quietly underneath everything you have ever touched. And strangely enough, this mystery connects beautifully with another journey we explored here on Velarin, Sleepy Space Mysteries. The story of what existed before the first stars awakened in the universe. Because both mysteries begin with the same unsettling possibility, that reality is far stranger beneath the surface than it appears from above. Far below the border between Switzerland and France, inside the enormous underground tunnels of CERN, particles are being accelerated to almost the speed of light before colliding with unimaginable force. For only the briefest instant, these collisions recreate conditions not seen since the earliest moments after the Big Bang. And hidden within the showers of particles produced by these collisions, physicists are beginning to notice something unusual. Tiny inconsistencies, small cracks, gentle whispers that perhaps the deepest theory humanity has ever created is not the final layer after all. Tonight, we will slowly descend into that mystery together. Before we continue, welcome to Velarin's Sleepy Space Mysteries, a quiet place for cosmic storytelling beneath the stars. If you enjoy these long, relaxing explorations into the universe, consider subscribing, leaving a like, turning on notifications, and perhaps joining the channel membership to help support future journeys into the unknown. And while you settle in tonight, let me know something simple and peaceful in the comments. Where in the world are you listening from tonight? Now dim the lights, relax your thoughts, and imagine shrinking smaller and smaller, past mountains, past grains of sand, past cells and molecules, descending deeper into matter itself. Because the deeper humanity has looked into reality, the stranger reality has become. There is something deeply unsettling about the history of science when you look at it slowly enough. Again and again, humanity becomes convinced it has finally reached the bottom layer of reality, only to discover another hidden world waiting underneath. Ancient civilizations once believed matter was continuous, smooth, and indivisible, like water flowing endlessly without structure. Then came the first whispers of atoms, tiny invisible building blocks too small for any eye to see. For a while, atoms seemed final, permanent, untouchable. The word itself meant uncuttable. But eventually atoms cracked open too, revealing electrons swirling around a dense nucleus hidden inside enormous empty space. Then the nucleus itself shattered into protons and neutrons. Later still, those particles dissolved into quarks, smaller entities confined by forces so strange they almost seem dreamlike. And now, standing here in the modern age beside machines powerful enough to recreate fragments of the early universe, physicists are beginning to suspect the pattern may be happening once again. That perhaps quarks and electrons are not truly fundamental either. That beneath the standard model itself, Another layer may be waiting quietly in the dark. To understand why this possibility is so disturbing to physicists, you first have to understand how successful the Standard Model actually is. It is difficult to exaggerate the precision of this theory. Every beam of light entering your eyes, every chemical reaction inside your body, every spark of electricity flowing through civilization, every star burning across the night sky, all of it can be described using a small collection of particles and forces organized inside a mathematical framework so accurate that its predictions match experiments to astonishing precision. Imagine predicting the distance between two cities with an error smaller than the width of a human hair. That is roughly the level of accuracy modern particle physics sometimes achieves. The Standard Model is not merely successful. It is almost frighteningly successful. And yet, despite its perfection, there are cracks. Far underground at CERN, inside the Large Hadron Collider, protons circle through a gigantic ring buried beneath the Earth. They travel faster and faster until they approach the speed of light itself, completing thousands of laps every second. Superconducting magnets colder than deep space bend their paths through tunnels stretching for nearly 27 kilometers. Then, at carefully chosen points, the beams collide head-on. The collisions are violent beyond ordinary comprehension. Tiny fragments of matter explode apart, releasing energies concentrated into spaces smaller than atoms. For the briefest instant, conditions resemble the universe less than a trillionth of a second after the Big Bang. It is not simply an experiment. It is humanity opening microscopic doorways into the earliest moments of existence. Most collisions produce exactly what the Standard Model predicts: familiar particle showers, expected decay patterns, clean mathematical agreement, but not always. Sometimes the detectors record something slightly unusual, particle appearing more often than expected, a decay unfolding at a subtly incorrect rate, a mass measurement shifted ever so slightly away from theory. None of these anomalies alone are large enough to overthrow physics. In fact, many disappear when more data arrives. But collectively they create a strange atmosphere within the field. A feeling that something unseen may be tugging gently on reality from beneath the surface. One of the reasons these tiny discrepancies matter so much is because of how quantum fields behave. Modern physics no longer views particles as little solid spheres moving through empty space. Instead, reality appears to be built from invisible fields stretching across the universe. The electron field exists everywhere. The quark fields exist everywhere. Even in perfect emptiness, these fields remain present, fluctuating softly like an endless ocean beneath existence itself. A particle is simply a ripple traveling through one of these fields. An electron is not a tiny object in the traditional sense. It is a localized vibration inside the electron field. A photon is a vibration in the electromagnetic field. matter itself begins to resemble music played across invisible cosmic instruments. And this is where the mystery deepens beautifully, because quantum fields are never completely still. Even empty space trembles. At every moment, particles briefly flicker into and out of existence within the vacuum itself. Tiny fluctuations emerge and vanish continuously beneath reality, too fast to observe directly yet powerful enough to influence measurable physics. Physicists call these temporary entities virtual particles, though the name is slightly misleading because their effects are very real. They subtly alter the masses and magnetic properties of known particles. They shift energy levels inside atoms. They create measurable forces inside pure vacuum. Empty space is not empty at all. It is restless, alive with hidden motion. Now imagine something extraordinary. Imagine there are additional fields beyond the standard model. Unknown particles, hidden forces, entire structures of reality humanity has not yet discovered. Even if these entities are too heavy or too difficult to create directly inside colliders, they would still influence the quantum vacuum. They would still whisper through these fluctuations. And those whispers could slightly alter the behavior of particles we can observe. This means physicists do not necessarily need to see a hidden particle directly in order to detect its presence. They only need to measure known particles with enough precision to notice the invisible fingerprints left behind. This is why modern physics has become obsessed with impossibly precise measurements. Scientists are no longer simply smashing particles apart hoping something dramatic appears. They are listening carefully to reality itself, searching for tiny deviations buried deep inside the mathematics. A particle behaving almost correctly, but not quite. A decay happening almost exactly as predicted, but shifted ever so slightly away from expectation. Because history has shown that revolutionary discoveries often begin this way. Not with explosions, not with certainty, but with faint inconsistencies quietly appearing at the edge of human understanding. And tonight, as we continue descending deeper beneath matter itself, we will follow those inconsistencies into the darkness. Because some physicists now believe they may be the first signs that reality contains another hidden layer beneath everything we currently know. The deeper physicists look into matter, the more reality begins to lose the qualities our human minds instinctively expect from the world. Solidity dissolves into emptiness. Particles blur into probabilities. Time itself behaves differently at microscopic scales. And somewhere inside this strange descent, one discovery in particular changed modern physics forever, because it revealed that the universe may be filled with something invisible that quietly shapes everything around us. This discovery was the Higgs field, and understanding it may help explain why scientists now suspect there are hidden layers still buried beneath the standard model. For most of human history, mass seemed simple. Objects felt heavy because they contained matter. Stones were heavier than feathers. Planets were heavier than stones. The question hardly seemed mysterious. But once physicists began studying fundamental particles, the mystery became unavoidable. Why do particles possess mass at all? Why is the electron light while the top quark is unimaginably heavy? Why do some particles move slower than light while photons remain forever massless, racing through the cosmos at the maximum speed reality allows? The Standard Model could describe these masses mathematically, but description is not explanation. Somewhere beneath the equations, something deeper appeared responsible. Then came an extraordinary realization during the 1960s. Several physicists working independently proposed that empty space itself might contain an invisible field stretching across the entire universe. Unlike other quantum fields, this field would never completely vanish, even in perfect vacuum. It would remain permanently active everywhere, like a hidden cosmic ocean filling all of existence. Particles moving through this field would interact with it differently depending on their nature. Some particles would pass through almost untouched. Others would become heavily entangled with it, as though dragged through invisible resistance. And this interaction would appear to us as mass. The idea sounded almost mystical at first, yet mathematically it worked beautifully. Imagine walking through water. Movement becomes slower, heavier, more difficult. Now imagine another person moving through empty air with almost no resistance at all. The Higgs field behaves somewhat like this invisible medium. Electrons interact lightly with the field and therefore acquire only a small mass. The top quark interacts intensely and becomes extremely heavy. Photons ignore the field entirely, remaining massless. The astonishing implication is that mass may not be an intrinsic property of matter at all. Instead, mass emerges from interaction. Matter becomes heavy because the universe itself quietly resists certain particles as they move through an invisible background field permeating all of space. And yet the story grows stranger, because the Higgs field is not simply sitting somewhere far away among galaxies. It exists here, right now, passing through your body, flowing through the walls around you, existing inside every atom in your brain as you listen to these words. The universe is immersed in it continuously, though human senses can never directly perceive it. Every physical object you have ever touched owes its solidity partly to this hidden field. For decades, the Higgs field remained theoretical. Beautiful mathematics, but unconfirmed. Physicists suspected it existed because without it, the equations of the Standard Model began collapsing into inconsistency. Certain particles should have behaved wildly differently. The weak nuclear force would become mathematically unstable. The universe itself would fail to resemble reality. But suspicion is not proof. To confirm the field existed, physicists needed to detect a ripple inside it, a temporary vibration known as the Higgs boson. That search became one of the primary reasons humanity built the Large Hadron Collider. Inside CERN, protons were accelerated through underground tunnels with unimaginable energy before colliding head-on. The hope was that enough concentrated energy might briefly disturb the Higgs field itself, creating a detectable particle before it decayed. The challenge was enormous because the Higgs boson survives for only an incredibly tiny fraction of a second before vanishing into other particles. Scientists could never observe it directly. Instead, they had to reconstruct its existence from the debris left behind after decay, like detectives reconstructing an invisible object from scattered fragments. Then, finally, in July of 2012, the announcement arrived. 2 separate experiments at CERN independently detected evidence for a new particle matching the predicted Higgs boson almost perfectly. After nearly half a century of searching, the hidden field responsible for mass had finally revealed itself. The discovery completed the Standard Model. Every major particle predicted by the theory had now been observed experimentally. For a brief moment, it seemed physics had reached an extraordinary triumph, perhaps even the final chapter in humanity's understanding of matter. But something unexpected happened afterward. The Higgs boson behaved too perfectly. Many physicists secretly hoped the particle would reveal obvious cracks in the Standard Model. Perhaps it would decay incorrectly. Perhaps its mass would appear unnatural. Perhaps it would point clearly toward entirely new physics beyond current understanding. Instead, the Higgs boson matched theoretical predictions with unsettling precision. Beautiful for the theory, frustrating for everyone hoping for revolutionary clues. And yet, beneath that disappointment lingered a deeper unease. Because even though the Standard Model appeared complete, physicists already knew it could not possibly describe all reality. The theory says nothing about dark matter, the invisible substance outweighing ordinary matter across the cosmos. Cannot explain why gravity refuses to fit into quantum mechanics. Cannot naturally explain neutrino masses. It cannot explain why the universe contains more matter than antimatter. In other words, the theory works astonishingly well, while simultaneously leaving some of the largest mysteries in existence completely unresolved. This contradiction has created a strange mood in modern physics. It is as though humanity has discovered a magnificent clockwork mechanism hidden beneath nature, only to realize entire sections of the machinery are still missing. The Standard Model predicts countless experiments correctly, yet enormous portions of reality remain outside its reach. And this is why physicists continue searching obsessively through collider data, precision measurements, and quantum anomalies. Because somewhere beneath these unexplained gaps may lie another hidden layer of existence, one deeper than quarks, deeper than fields, perhaps even deeper than space itself. And the first whispers of that hidden layer may already be appearing inside the smallest imperfections in the equations. If there truly is another hidden layer beneath the Standard Model, physicists believe it will not reveal itself dramatically at first. Reality rarely tears open all at once. More often, nature whispers through tiny inconsistencies so small they almost disappear beneath noise. Particle measured slightly heavier than expected. A magnetic field behaving imperfectly. A decay occurring too often, or not often enough. To most people, these discrepancies sound insignificant, but inside particle physics they can become the first faint fingerprints of entirely new realms of existence. And among all the modern anomalies haunting physics, few have generated more fascination than the strange behavior of a particle called the muon. At first glance, the muon appears almost identical to the electron, carries the same electric charge. It responds to the same forces. It behaves similarly inside magnetic fields. But there is one profound difference. The muon is much heavier, more than 200 times heavier than the electron. And this extra mass makes it extraordinarily sensitive to hidden physics lurking inside the quantum vacuum. In a sense, the muon behaves like a deeper probe into reality itself, almost as though nature accidentally provided physicists with a slightly heavier flashlight capable of illuminating structures ordinary electrons cannot easily detect. To understand the mystery surrounding the muon, imagine a tiny spinning compass floating through space. Charged particles possess an intrinsic property called spin, and because of this spin they behave somewhat like microscopic magnets. When placed inside a magnetic field, they wobble and rotate in highly predictable ways. According to the equations of quantum mechanics, the exact speed of this wobble can be calculated with astonishing precision. But there is a complication. The muon does not exist alone. As it moves through space, it constantly interacts with invisible quantum fluctuations surrounding it. Remember the restless vacuum we explored earlier. Empty space is filled with fields trembling softly beneath existence. Virtual particles emerge briefly, vanish, and reappear continuously. The muon interacts with all of them. Tiny clouds of invisible particles surround it constantly, subtly altering its magnetic behavior. The standard model predicts exactly how large these alterations should be. Every known particle contributes slightly to the muon's motion, like invisible currents tugging gently at a drifting boat. For decades, physicists have measured this effect with extraordinary care. The quantity itself has an intimidating technical name, the anomalous magnetic moment of the muon, but the essential idea is simple. Scientists measure how the muon actually wobbles inside a magnetic field and compare the result to the theoretical prediction. If the numbers disagree even slightly, it may mean unknown particles are influencing the muon from beyond the standard model. And remarkably, that disagreement appeared to emerge. The experiment itself feels almost surreal. At Fermilab in Illinois, scientists use a gigantic circular magnetic ring nearly 15 meters across. Muons are accelerated into this ring at tremendous speed, where they circle thousands of times inside an exquisitely controlled magnetic environment. Sensors carefully track how the muons wobble during their brief existence before decaying into other particles. Every detail must be controlled with unbelievable precision. Tiny temperature shifts, magnetic fluctuations, microscopic detector effects, all of them matter. The experiment became so delicate that even transporting the magnetic ring itself across America years earlier required an extraordinary journey by barge and truck because the structure was too fragile to disassemble. Then came the measurements. For years, experimental data suggested the muon's magnetic behavior did not perfectly match the standard model prediction. The discrepancy was small, but persistent. Again and again, the measured value drifted slightly away from theory, as though invisible particles were subtly influencing the quantum vacuum surrounding the muon. The possibility electrified the physics community because if confirmed, it would mean humanity had finally detected direct evidence for physics beyond the standard model. The implications were staggering. Some physicists proposed hidden particles interacting through undiscovered forces. Others imagined supersymmetry, a theoretical framework where every known particle possesses an unseen partner particle hidden at higher energies. Some theories suggested entirely new quantum fields permeating space. Suddenly, the muon became more than a particle. It became a messenger from deeper reality. But science is cautious by necessity. As measurements improved, theorists realized something troubling. Calculating the standard model prediction itself was more difficult than expected because certain contributions involving the strong nuclear force remained incredibly complicated. Different mathematical approaches produced slightly different theoretical values. Some calculations preserved the anomaly beautifully. Others reduced it significantly. The closer scientists looked, the more uncertain the situation became. And this uncertainty reveals something important about modern physics. At the frontiers of knowledge, certainty almost never arrives cleanly. Reality resists simple answers. Experiments improve. Theories evolve. Data shifts. Entire careers can unfold inside the tension between two decimal places. To outsiders, this may sound frustrating, but in truth, it is deeply human. Science is not a machine delivering absolute truth instantly. It is a slow conversation between humanity and the universe, one measurement at a time. Yet despite the uncertainty, the muon anomaly continues haunting physics because it embodies a deeper pattern now appearing across multiple experiments. Tiny discrepancies, small tensions, gentle statistical irregularities that refuse to disappear completely. None alone are enough to overthrow the standard model. But together they create a strange atmosphere, almost like hearing distant echoes beneath the floorboards of reality. And perhaps the most unsettling part is this. If these anomalies are real, then whatever lies beneath the standard model may already be influencing our world constantly without our awareness. Invisible fields may be surrounding us right now. Hidden particles may flicker silently through the vacuum of space. Entire layers of existence could be woven invisibly through ordinary reality while human senses remain completely blind to them. This possibility changes the emotional texture of the universe itself. Because the cosmos no longer feels empty or finished. Instead, it begins to resemble an unfinished structure whose deeper foundations remain concealed beneath darkness. Humanity may have mapped the visible surface of physics with astonishing precision while still remaining almost entirely ignorant of the deeper architecture supporting it all. And as physicists continue listening carefully to these whispers from the quantum world, Another mystery has begun emerging from deep inside CERN itself, a mystery involving particles called mesons, whose strange decays may be hinting that nature's fundamental forces do not behave quite as evenly as the standard model insists they should. There is a quiet beauty in the way the universe hides its deepest truths, not behind walls or locked doors, but inside patterns so subtle they can remain invisible for decades. Sometimes an entire revolution in physics begins with a number that appears slightly too large or slightly too small. A tiny asymmetry hidden inside enormous oceans of data. And this is precisely why physicists became fascinated by an unusual family of particles known as mesons, because buried within their decays there appeared to be hints that nature itself might not behave as symmetrically as the standard model demands. Mesons are unstable particles containing a bottom quark bound together with a lighter quark. They do not exist naturally for long because they decay almost instantly into other particles through the weak nuclear force. Yet despite their brief existence, they are incredibly valuable to physicists because their decays are extraordinarily sensitive to hidden quantum effects. Tiny unknown particles, even ones too massive to create directly inside colliders, can subtly influence how mesons transform and decay. In this sense, mesons behave almost like delicate instruments capable of sensing invisible disturbances deep inside the quantum vacuum. At CERN, one experiment in particular became devoted to studying these decays with astonishing precision. The experiment is called LHCb, and unlike the enormous general-purpose detectors searching broadly for new particles, LHCb focuses specifically on the behavior of particles containing heavy quarks. It watches how they decay, how often they transform into certain products, and whether those transformations obey the precise mathematical symmetries predicted by the standard model. One of the most important of these symmetries is something called lepton universality. The name sounds intimidating, but the underlying idea is surprisingly elegant. According to the standard model, the weak nuclear force should treat electrons and muons almost identically. Aside from their different masses, they should behave the same way under fundamental interactions. Nature, in theory, should not prefer one over the other. If a meson decays into electrons a certain percentage of the time, it should decay into muons at nearly the same rate after accounting for mass differences. The equations are extraordinarily specific about this balance. But then the measurements began arriving. Around the mid-2010s, physicists studying meson decays noticed something peculiar. Certain decay processes appeared to produce muons slightly less often than expected compared to electrons. The discrepancy was not enormous. In fact, it was tiny, but it persisted through multiple analyses and multiple years of data. The numbers consistently leaned in the same strange direction, almost as though the universe subtly favored electrons over muons in ways the standard model could not explain. The implications were enormous. If lepton universality truly failed, then the standard model would be fundamentally incomplete. Some unknown influence would have to be interfering with the weak nuclear force itself. physicists immediately began constructing theories to explain the anomaly. Some imagined undiscovered particles called leptoquarks, strange entities capable of connecting quarks and leptons through entirely new interactions. Others proposed new force-carrying bosons, heavier cousins of familiar particles already known to physics. Suddenly, the quiet statistical irregularity inside B meson decays became one of the most exciting mysteries in the entire field. For several years, anticipation grew steadily. Theoretical papers multiplied across physics journals. Conferences filled with discussion. Researchers wondered whether CERN was finally approaching direct evidence for a hidden layer beneath the standard model. Some physicists even began cautiously imagining that the first confirmed doorway into new physics might emerge not from discovering a dramatic new particle, but from detecting subtle imbalances hidden inside quantum decays. Then reality shifted again. As more data accumulated and analysis techniques improved, the anomaly began weakening. New measurements moved closer to the standard model predictions. The once exciting discrepancies gradually shrank. By the early 2020s, several of the most famous anomalies had largely faded into statistical uncertainty. What once looked like a possible revolution now appeared far less certain. To outsiders, this might sound disappointing, but something important hides inside moments like this. Science advances not only through discoveries, but through elimination. Every anomaly forces physicists to sharpen experiments, refine calculations, and understand nature more deeply. Even disappearing mysteries leave behind improved knowledge. Yet, interestingly, not all tensions within B meson physics vanished completely. Some subtle discrepancies still remain inside angular decay patterns and branching ratios, small enough to remain uncertain, yet persistent enough that physicists continue watching carefully. And this ongoing uncertainty creates an atmosphere unlike anything else in science. Because particle physics today exists in a strange emotional state suspended between triumph and frustration. The standard model continues passing experiment after experiment with extraordinary success, yet physicists know with absolute certainty that it cannot be the final story. Dark matter still surrounds galaxies invisibly. Gravity still refuses to merge cleanly with quantum theory. Neutrinos still possess mysterious tiny masses. The universe itself still contains profound, unanswered questions. So every small anomaly becomes emotionally charged. Every discrepancy carries the possibility that perhaps, finally, the next hidden layer is beginning to reveal itself. But perhaps the deepest mystery of all lies not inside collider experiments, but in the cosmos itself. Because when astronomers observe galaxies rotating through space, something impossible appears to happen. Stars at the outer edges move far too quickly, as though invisible mass surrounds them. Galaxy clusters bend light more strongly than visible matter alone can explain. Across the universe, gravity behaves as though enormous quantities of hidden matter exist everywhere, silently shaping cosmic structure while remaining completely invisible to human eyes. and the Standard Model offers no answer. None of its particles can explain this missing mass. No known field accounts for it. According to everything modern cosmology can measure, ordinary matter, the atoms inside stars, planets, oceans, trees, and human bodies, makes up only a small fraction of reality. Most of the universe appears to consist of something unknown, something dark, something hidden. This realization changes the emotional scale of the mystery completely. The hidden layer physicists are searching for may not merely be another tiny particle inside colliders. It may represent an entirely unseen sector of reality surrounding galaxies themselves. A cosmic architecture woven invisibly through space-time while ordinary matter drifts like illuminated dust upon its surface. And if that is true, then humanity may currently understand only a thin visible fraction of existence, while the vast majority of reality remains concealed beneath the surface, waiting silently in darkness for the moment we finally learn how to see it. There is something almost humbling about realizing that the stars, galaxies, and glowing nebulae filling the night sky may represent only a tiny visible fragment of reality. Human beings evolved beneath sunlight and firelight, so naturally we tend to trust what can be seen. We imagine the universe as a grand collection of luminous objects scattered across empty darkness. But modern cosmology has revealed something profoundly unsettling. The visible universe, all ordinary matter made from atoms, planets, oceans, trees, human bodies, and distant suns, appears to account for only a small percentage of existence. Most of reality may be hidden from us entirely. This realization emerged slowly through decades of astronomical observation. During the early 20th century, astronomers began carefully measuring how galaxies rotate. At first, the expectation seemed obvious. Stars near the crowded centers of galaxies should orbit rapidly because enormous amounts of visible matter are concentrated there. Meanwhile, stars farther outward should move more slowly. Much like planets in our solar system travel more gradually the farther they are from the sun, gravity weakens with distance, so outer stars should drift calmly around galactic edges. But that is not what astronomers observed. Instead, stars at the outer edges of galaxies were moving far too quickly. According to visible matter alone, many galaxies should have flown apart long ago. Yet they remained stable, rotating as though vast amounts of invisible mass surrounded them. At first, scientists suspected measurement errors. Perhaps telescopes were inaccurate. Perhaps assumptions about galactic structure were flawed. But the evidence continued accumulating across decade after decade. Everywhere astronomers looked, gravity appeared stronger than visible matter could explain. Then the mystery deepened further. In massive galaxy clusters, light from distant galaxies bends while passing nearby, distorted by gravity itself. This phenomenon, called gravitational lensing, acts almost like cosmic glass, warping the appearance of the universe behind it. By measuring these distortions, astronomers can estimate how much mass exists inside galaxy clusters. And once again, the calculations produced an impossible result. There was vastly more gravity present than visible matter alone could generate. Something invisible was shaping the cosmos. Something enormous. Something everywhere. Today, physicists call this hidden substance dark matter, though the name itself is strangely misleading because nobody truly knows what dark matter is. The term simply means matter that does not interact with light in ordinary ways. It does not glow. It does not reflect. It does not absorb radiation like familiar atoms. Yet gravity reveals its presence unmistakably. Galaxies appear embedded inside gigantic halos of invisible mass extending far beyond visible stars, almost like luminous islands floating within vast oceans of hidden structure. And this is where the mystery collides directly with particle physics. Because the standard model cannot explain dark matter at all. None of its known particles possess the right properties. Neutrinos exist in enormous numbers throughout the universe, but they are too light and move too quickly to account for observed cosmic structures. Ordinary atoms are ruled out because astronomers can precisely measure how much atomic matter formed after the Big Bang. The numbers simply do not work. According to current evidence, dark matter must consist of entirely new particles beyond the standard model. This realization is one of the strongest reasons physicists believe another hidden layer of reality exists beneath current understanding. Some researchers imagine heavy particles drifting silently through galaxies, interacting almost entirely through gravity. Others propose invisible sectors of physics containing entire families of particles hidden from ordinary matter. Some theories suggest dark matter may consist of ultralight quantum fields spread across enormous cosmic distances, behaving less like particles and more like waves rippling through space-time itself. There are even proposals that dark matter may involve dimensions or structures humanity has not yet learned how to perceive directly. What makes the mystery emotionally powerful is how close dark matter may already be. Right now, as you listen quietly beneath the night sky, countless dark matter particles may be passing through your body every second, through the earth, through the walls around you, through entire planets and stars without leaving noticeable traces. Humanity could be immersed inside a hidden cosmic ocean while remaining almost completely blind to it. And physicists have tried desperately to detect it. Deep underground laboratories have been built beneath mountains to shield experiments from cosmic radiation and ordinary particle noise. Inside enormous tanks filled with ultra-pure liquids, scientists wait silently for the faintest possible interaction between dark matter and ordinary atoms. Some experiments search for tiny flashes of light produced by invisible collisions. Others attempt to detect minute vibrations or temperature changes. Yet, despite decades of searching, no direct detection has been confirmed. Meanwhile, CERN continues another strategy entirely. Inside the Large Hadron Collider, physicists hope that enough collision energy might briefly create dark matter particles directly. Since such particles would likely pass invisibly through detectors, scientists search instead for missing energy, moments where collisions appear to lose momentum mysteriously, as though unseen entities escaped the experiment unnoticed. So far, the results remain inconclusive. The hidden layer, if it exists, continues evading capture. But perhaps even more mysterious than dark matter is another problem quietly haunting cosmology. The universe itself should not exist, at least not in the form we observe today. According to the laws of physics, the Big Bang should have created matter and antimatter in nearly equal quantities. Antimatter behaves almost exactly like ordinary matter except with opposite electric charge. When matter and antimatter meet, they annihilate each other completely, converting into pure energy. If equal amounts formed during the birth of the universe, then nearly everything should have vanished in enormous bursts of radiation long ago. And yet matter survived. Stars formed, galaxies emerged, planets cooled, oceans appeared, life awakened. Somehow, in the earliest moments after the Big Bang, nature favored matter ever so slightly over antimatter. For roughly every billion antimatter particles, there were perhaps 1,000,000,001 matter particles. That tiny imbalance became everything we know today after all the remaining particles annihilated each other away. But the Standard Model cannot adequately explain why this imbalance occurred. Once again, another enormous gap appears inside our understanding. And slowly, almost uncomfortably, a pattern begins emerging. Dark matter unexplained. Antimatter asymmetry unexplained. Gravity incompatible with quantum mechanics. Hidden anomalies inside precision measurements. Everywhere physicists look, reality appears to contain missing pieces. It is as though humanity has assembled a magnificent map of nature while entire continents remain absent from the parchment, which raises a haunting possibility. Perhaps the Standard Model is not the foundation of reality at all. Perhaps it is only the visible surface of a much deeper structure still concealed beneath existence itself, waiting patiently for humanity to descend one layer further into the dark. Perhaps the strangest part of modern physics is not that the universe contains mysteries, but that reality appears mathematically incomplete in ways humanity can clearly recognize. Physicists are not wandering blindly through darkness without direction. They can see the missing pieces indirectly, almost like noticing empty spaces inside a puzzle where certain shapes obviously belong. Gravity does not fit cleanly into quantum theory. Dark matter surrounds galaxies invisibly. Matter itself somehow survived the early universe when it should have annihilated away. And beneath all of these mysteries lies another profound question, one that may ultimately lead deeper than particles, fields, or even space-time itself. Why does reality obey mathematics so perfectly at all? The more physicists uncover about the universe, the more nature resembles an immense hidden architecture built from elegant mathematical relationships. Equations discovered on chalkboards somehow describe stars, atoms, black holes, and quantum fields with astonishing precision. Entire phenomena can be predicted decades before experiments confirm them. The Higgs boson existed mathematically long before humanity observed it physically. Gravitational waves were predicted by Einstein a century before detectors finally heard them ripple through spacetime. Again and again, mathematics seems to glimpse structures hidden beneath reality before instruments can physically reveal them. This has led some physicists to suspect that the universe may be far stranger than ordinary intuition allows. One possibility is that the particles we currently call fundamental are not truly fundamental at all. Quarks and electrons may themselves contain deeper internal structure impossible to observe with present technology. History offers a powerful warning here. Atoms once appeared indivisible until better experiments revealed nuclei and electrons inside them. Protons later appeared elementary until quarks were discovered hidden within. Each time humanity declared a final layer had been reached, nature quietly revealed another beneath it. Some physicists wonder whether the same pattern continues indefinitely. One proposed idea is called prion theory. According to this concept, quarks and leptons may be composed of even smaller entities called prions, hidden building blocks beneath the standard model itself. In these theories, the particles we observe today would resemble atoms in earlier centuries, not fundamental objects, but composite structures built from something deeper. If true, the standard model might represent only an intermediate layer of reality rather than the true foundation. But detecting such structure would be extraordinarily difficult. The Large Hadron Collider already probes distances unimaginably small, thousands of times smaller than atomic nuclei. If quarks possess hidden internal components, those scales may lie far beyond humanity's current experimental reach. Physicists search indirectly instead, looking for tiny deviations in particle collisions, subtle hints that supposedly point-like particles may possess hidden size or internal dynamics. So far, no confirmed evidence has appeared. Yet the possibility remains open, waiting silently beyond current limits. Another, even stranger possibility involves extra dimensions. To human senses, the universe appears to contain 3 dimensions of space and 1 dimension of time. Length, width, height, and temporal flow. This structure feels natural because it matches ordinary experience. But some modern theories suggest reality may contain additional spatial dimensions curled invisibly beyond perception. These dimensions might be extraordinarily tiny, folded into microscopic scales impossible to observe directly. At first, this idea sounds fantastical, almost dreamlike. Yet mathematically it emerges naturally in several attempts to unify physics. String theory, perhaps the most famous example, proposes that fundamental particles are not tiny points at all, but microscopic vibrating strings existing within higher dimensional space. Different vibrational patterns produce different particles, much like different musical notes emerge from vibrating violin strings. Electrons, quarks, photons, and other particles would simply represent different resonances of underlying strings vibrating through hidden dimensions beyond ordinary perception. What makes this idea emotionally fascinating is how radically it transforms the concept of reality itself. Space would no longer be empty emptiness. Instead, existence would resemble a multidimensional fabric whose deeper geometry generates everything we observe. Matter, forces, and perhaps even consciousness could emerge from hidden structures folded invisibly beneath ordinary spacetime. And yet there is a problem. Despite decades of work, no direct experimental evidence for string theory or extra dimensions has been confirmed. The mathematics is beautiful, elegant beyond words in some cases, but nature has not yet revealed whether these hidden dimensions physically exist. This tension between mathematical beauty and experimental silence has become one of the defining emotional struggles of modern theoretical physics. Still, physicists continue searching because another mystery keeps pulling them deeper. Gravity. Among all known forces, gravity behaves uniquely. The Standard Model successfully describes electromagnetism, the weak force, and the strong nuclear force through quantum fields. But gravity resists quantization stubbornly. Whenever physicists attempt to describe gravity using ordinary quantum methods, the equations produce infinities that destroy predictive meaning. It is almost as though gravity belongs to a deeper layer of reality operating under fundamentally different rules. This incompatibility becomes especially important inside black holes and during the earliest moments of the Big Bang. In those extreme environments, quantum mechanics and gravity should both dominate simultaneously, yet current physics cannot merge them consistently. The equations break apart precisely where reality becomes most extreme. And this raises an unsettling possibility. Perhaps space-time itself is not fundamental. Some physicists now suspect that space and time may emerge from deeper quantum structures beneath reality, much like temperature emerges from molecular motion. From everyday experience, temperature feels fundamental. Yet deeper analysis reveals it is actually a collective effect arising from countless invisible particles moving together. In the same way, space-time itself may emerge from hidden quantum relationships existing underneath ordinary geometry. If true, then the universe may be vastly stranger than humanity has ever imagined. Space may not truly be continuous. Time may not flow fundamentally. Reality could be built from underlying informational structures, quantum entanglements, or microscopic geometries invisible to ordinary perception. The smooth universe humans experience might resemble a surface illusion generated by deeper hidden architecture beneath existence itself. And quietly, almost poetically, modern physics has begun circling toward an ancient philosophical idea: that reality is not what it first appears to be. The atoms beneath matter became fields. The fields became fluctuations. Space-time itself may become emergent. Every layer humanity uncovers seems to dissolve into something stranger underneath. It is as though the universe continuously retreats deeper into abstraction whenever we approach what appears to be the final truth. Yet perhaps that endless descent is not failure. Perhaps it is the nature of reality itself. And somewhere beneath these mysteries, beneath quantum fields and hidden dimensions and dark matter halos surrounding galaxies, physicists continue listening carefully for the faint whispers suggesting that another unseen layer still waits below, patient, silent, and almost close enough to touch. The deeper modern physics descends into reality, the more the universe begins to resemble something unfinished, something layered far beyond ordinary perception. And perhaps nowhere is this feeling stronger than at the boundary between quantum mechanics and gravity, because it is here that humanity's two greatest theories stop cooperating with each other entirely. Quantum mechanics governs the microscopic world with astonishing precision. General relativity describes gravity, black holes, and the motion of galaxies across cosmic distances. Individually, both theories work beautifully. Yet when physicists attempt to combine them into one complete description of reality, the equations collapse into contradiction. This conflict is not small. It is one of the deepest crises in all of science. To understand why, imagine the universe at two vastly different scales. In the ordinary world of planets and stars, gravity behaves smoothly. Massive objects bend spacetime itself, and smaller objects follow those curves naturally. Einstein described this process not as a traditional force pulling objects together, but as geometry. The Earth orbits the Sun because spacetime around the Sun becomes curved. Matter tells spacetime how to bend, and spacetime tells matter how to move. The theory is elegant, almost poetic in its simplicity. And remarkably, it works. General relativity correctly predicts the motion of planets, the bending of light near massive objects, the expansion of the universe, and even the existence of black holes. A century after Einstein proposed it, experiments continue confirming its predictions with extraordinary precision. Massive observatories have now directly detected gravitational waves rippling through spacetime itself from colliding black holes billions of light-years away. Einstein's vision of gravity remains one of humanity's greatest intellectual achievements. But quantum mechanics describes reality completely differently. At microscopic scales, certainty dissolves into probability. Particles behave like waves. Empty space fluctuates restlessly. Events become uncertain until measured. Instead of smooth geometry, quantum theory reveals a jittering universe filled with fluctuations and discrete interactions. And unlike gravity, quantum mechanics treats forces as exchanges of particles through fields woven across space. For decades, physicists assumed gravity should eventually fit into this framework too. If electromagnetism possesses a force-carrying particle called the photon, perhaps gravity possesses one as well, a hypothetical particle called the graviton. The idea seems reasonable at first, but when researchers attempt to construct a quantum theory of gravity using ordinary techniques, infinities appear everywhere. The mathematics explodes uncontrollably. Predictions lose meaning. It is almost as though space-time itself refuses to behave quantum mechanically in the way physicists expect. This becomes especially disturbing inside black holes. Black holes are regions where gravity becomes so intense that space-time curves inward catastrophically. According to general relativity, matter collapsing inside a black hole eventually compresses toward a singularity, a point of effectively infinite density where space-time itself breaks apart mathematically. Infinity appears once again. The equations stop making physical sense. General relativity predicts its own failure deep inside black holes. And near the beginning of the universe, the same problem returns. If we rewind cosmic history backward through time, the universe becomes denser, hotter, and smaller. Eventually, the equations approach another singularity, the Big Bang itself. Once again, space-time reaches infinite density. Once again, physics collapses. Humanity's theories cannot fully describe the earliest moment of existence, which means something extraordinary. The deepest foundations of reality remain unknown, and this realization has led some physicists toward a radical possibility. Perhaps gravity is not simply another force waiting to be quantized. Perhaps space-time itself emerges from deeper, hidden structures beneath reality. Maybe the universe resembles a projection rising from microscopic quantum information invisible to ordinary perception. One clue pointing toward this possibility comes from black hole entropy. During the 1970s, physicists Jacob Bekenstein and Stephen Hawking made a shocking discovery. Black holes are not perfectly black. Quantum effects near their event horizons cause them to emit faint radiation slowly over enormous timescales. This became known as Hawking radiation. But the calculations revealed something even stranger. The information content inside a black hole appeared related not to its volume, but to the surface area of its event horizon. This idea sounds abstract at first, but its implications are profound. Normally, we expect information to scale with volume. A larger room can hold more objects than a smaller one. But black holes behave differently. Their information seems encoded on surfaces, almost like a hologram. This observation eventually inspired the holographic principle, the astonishing proposal that the universe itself may function holographically, where the three-dimensional reality humans experience emerges from deeper information encoded on lower-dimensional boundaries. If true, then space itself may not fundamentally exist in the way human intuition imagines. Distance, geometry, volume, perhaps all emerge from hidden quantum relationships beneath perception. Reality may be built not from matter moving through space-time, but from information generating space-time itself. In this vision, the universe begins resembling an immense cosmic code unfolding into the appearance of physical existence. And strangely enough, experiments at CERN may indirectly help probe these mysteries too. Whenever particles collide at enormous energies, they briefly recreate conditions approaching those of the early universe. The deeper physicists push into high-energy physics, the closer they move towards scales where gravity and quantum mechanics may finally intersect. Some theories predict microscopic black holes might appear during extremely energetic collisions if hidden dimensions exist. Others suggest entirely new quantum gravitational effects could subtly influence particle behavior. So far, no confirmed signals have emerged, but the search continues patiently. What makes this search emotionally powerful is that humanity may currently stand at the edge of another intellectual transformation comparable to the discoveries of atoms or relativity itself. The next hidden layer beneath matter may not merely reveal new particles. It may force humanity to rethink the nature of space, time, and existence altogether. And perhaps the most beautiful part of this journey is how it changes our relationship with the cosmos emotionally. For centuries, humans feared mystery because mystery represented ignorance. But modern physics has transformed mystery into something else entirely. The unknown is no longer emptiness. It is structure waiting beyond current understanding. Every unanswered question becomes evidence that reality contains greater depth than we previously imagined. The universe is not becoming smaller as science advances. It is becoming stranger, more layered, more profound, and somewhere beneath quantum fields, dark matter halos, hidden dimensions, and the trembling fabric of space-time itself, physicists continue listening carefully for the next whisper from reality. The faint signal suggesting that beneath everything humanity currently understands, another deeper layer still waits silently in the dark. There is a moment that often comes late at night, especially after thinking too long about the universe, when reality begins to feel strangely thin. Familiar objects no longer seem entirely solid. The room around you becomes less certain somehow, as though the ordinary world is only a surface layer covering something far deeper and infinitely stranger underneath. Modern physics creates this feeling not because it destroys wonder, but because it reveals how incomplete ordinary perception truly is. Human senses evolved to survive on a small planet beneath a yellow star, not to comprehend quantum fields, dark matter, or the hidden architecture of space-time itself. And perhaps the greatest lesson emerging from CERN and modern cosmology is that reality may extend far beyond the narrow slice of existence humans naturally experience. Even now, physicists continue building increasingly sensitive experiments to probe these hidden layers. The Large Hadron Collider is preparing future upgrades that will dramatically increase the number of particle collisions recorded over coming years. New detectors are being designed to measure particle interactions with even greater precision. Underground observatories continue listening for dark matter. Giant telescopes map invisible gravitational structures across the cosmos. Everywhere humanity turns its instruments, the same quiet question echoes beneath the data. What lies underneath? And yet, despite all the extraordinary technology involved, the search itself remains deeply philosophical. Because every attempt to uncover a deeper layer of reality forces humanity to confront the limits of understanding itself. Consider for a moment how strange it truly is that the universe can be understood at all. Tiny creatures evolving on the surface of one small world somehow learn to split atoms, detect black holes, and measure fluctuations in quantum fields. Human brains composed of biological cells can construct mathematical equations capable of describing stars billions of light-years away. This fact alone borders on miraculous. The universe produced conscious beings capable of reflecting upon the universe itself. And perhaps this is why the search for deeper reality feels emotionally powerful in ways beyond ordinary science. It is not merely about particles. It is about humanity attempting to understand its own place inside existence. For centuries, each scientific revolution changed how humans viewed themselves. Copernicus revealed Earth was not the center of the cosmos. Darwin revealed humanity evolved alongside other life rather than standing apart from nature. Modern cosmology revealed galaxies are scattered across unimaginable distances within an expanding universe nearly 14 billion years old. And now quantum physics reveals that even matter itself is not solid in the way human intuition assumes. The next hidden layer may transform our perspective once again. Imagine for a moment that dark matter is finally identified. Suppose physicists discover an entirely new sector of particles existing alongside ordinary matter, invisible yet dominating the structure of galaxies. Humanity would suddenly realize that everything familiar, every mountain, ocean, animal, and star, represents only a minority component of cosmic reality. The visible universe would become something like illuminated foam floating atop a much larger unseen ocean. Or imagine if space-time itself proves emergent. If future theories reveal that space and time arise from deeper quantum information beneath reality, then the physical world humans experience may resemble a kind of projection generated from hidden structures impossible to perceive directly. Distance, motion, perhaps even causality itself could become secondary phenomena rather than fundamental truths. And perhaps most unsettling of all is another possibility quietly discussed among physicists and philosophers alike. What if there is no final layer? What if every discovery simply reveals another deeper structure underneath, endlessly? Atoms contained nuclei. Nuclei contained quarks. Quarks may contain deeper constituents. Fields may emerge from information. Space-time may emerge from quantum geometry. Perhaps reality is not built upon a final indivisible foundation at all. Perhaps existence resembles an infinite descent of hidden layers, each one generating the appearance of the layer above it. There is something strangely beautiful about this possibility. Human beings naturally long for final answers because certainty feels comforting. Yet the universe may not be constructed to provide ultimate closure. Instead, reality may be fundamentally open-ended, an endless unfolding mystery where every solved question creates new deeper ones beneath it. In that sense, science is not a journey toward an endpoint. It is a continuous descent into greater wonder. And still, despite all these uncertainties, physicists continue searching because small clues keep appearing. Tiny anomalies, persistent tensions, strange whispers buried inside measurements. The standard model remains astonishingly successful, yet subtle cracks continue surfacing along its edges. Most may eventually disappear with better data. Some already have. But history has shown repeatedly that reality often announces revolutionary discoveries quietly at first. A tiny discrepancy in Mercury's orbit eventually helped lead to general relativity. Small irregularities in atomic spectra helped launch quantum mechanics. Invisible missing mass revealed dark matter. Perhaps the next revolution is already beginning now, hidden inside numbers humanity barely notices. Far underground at CERN, proton beams continue racing through enormous tunnels beneath the Earth. Deep beneath mountains, dark matter detectors wait silently in darkness. Across the cosmos, telescopes observe galaxies bending light through invisible gravitational structures. Everywhere, humanity is listening carefully to the universe, searching for the next whisper from beneath reality's surface. And perhaps that is the most extraordinary part of all. Not that the universe contains hidden layers, but that conscious beings emerged capable of searching for them. Tonight, as the stars drift quietly overhead and the world grows still around you, imagine the invisible structures flowing silently through existence. Quantum fields trembling beneath matter. Dark matter surrounding galaxies like unseen cosmic skeletons. Space-time itself bending softly around stars and black holes. Hidden dimensions perhaps folded invisibly beyond perception. Vast layers of reality existing beyond ordinary senses while humanity slowly, patiently learns how to glimpse them. The universe is not becoming simpler as science advances. It is becoming deeper, and somewhere beyond the reach of today's equations, beyond the standard model, beyond the visible architecture of matter itself, another hidden layer may already be waiting silent and ancient, surrounding us completely while we drift through it unaware beneath the endless cosmic night. Long before humanity built particle colliders or wrote equations describing quantum fields, ancient people looked upward into the night sky and felt something they could not fully explain. A quiet awareness that reality possessed hidden depth. The stars moved with impossible precision. The moon changed shape predictably. Seasons returned in endless cycles. Beneath the visible world, there seemed to exist an invisible order guiding everything silently from behind the curtain of appearances. Thousands of years later, modern physics has arrived at a strangely similar feeling, except now the mystery extends not only outward into the cosmos, but inward beneath matter itself. And perhaps this is why the search for hidden layers beneath reality feels so emotionally powerful. It reconnects modern science with one of humanity's oldest instincts, the sense that existence contains more than what can immediately be seen. At CERN, inside underground chambers filled with superconducting magnets and colossal detectors, physicists continue recreating microscopic echoes of the early universe. Every second, millions upon millions of collisions erupt inside the Large Hadron Collider. Tiny particles smash apart with extraordinary violence, briefly releasing conditions similar to those that existed shortly after the Big Bang itself. Most of the resulting data confirms existing theories beautifully. Yet hidden inside this ocean of information, scientists continue searching for the rare events that refuse to fit neatly into current understanding. What makes this search remarkable is how patient it must be. Hollywood often portrays science as sudden revelations and dramatic breakthroughs, but real discovery usually unfolds slowly. Quietly, a discrepancy appears, then vanishes. Another anomaly survives slightly longer. Years pass. More data accumulates. Instruments improve. Theoretical calculations evolve. Entire generations of scientists may spend decades pursuing tiny irregularities buried inside incomprehensible quantities of information. The process resembles listening for faint whispers during a storm, and still they continue listening. One reason physicists remain hopeful is because the Standard Model itself contains clues suggesting incompleteness. Certain numerical relationships inside the theory appear strangely delicate, almost unnaturally balanced. The Higgs boson, for example, possesses a mass that many physicists consider mysteriously small compared to the enormous quantum corrections expected from deeper physics. This puzzle is sometimes called the hierarchy problem. According to ordinary quantum calculations, the Higgs field should naturally acquire vastly larger energies due to interactions with virtual particles fluctuating through the vacuum. Yet somehow it does not. Something appears to stabilize the Higgs field with astonishing precision. Some theorists believe the stability hints at hidden particles or symmetries beyond the Standard Model. Supersymmetry became one of the most famous proposed solutions. In supersymmetric theories, every known particle possesses an unseen partner particle with slightly different quantum properties. Electrons would have selectrons. Quarks would have squarks. Photons would have photinos. These hidden partners could mathematically cancel dangerous quantum corrections affecting the Higgs field, preserving the observed structure of reality naturally. For years, many physicists expected the Large Hadron Collider to discover supersymmetric particles quickly. But the collisions came, and no clear evidence appeared. As years passed, the absence of supersymmetry became increasingly unsettling. Some physicists began abandoning the idea entirely. Others proposed that supersymmetric particles may simply exist at higher energies still beyond experimental reach. The uncertainty deepened the strange atmosphere surrounding modern physics. Nature continued withholding clear answers, and yet hidden possibilities remain everywhere. Some researchers now suspect dark matter itself may belong to an entire invisible sector of reality, almost like a shadow universe existing alongside ordinary matter. This hidden sector could contain its own particles, forces, and interactions almost completely isolated from familiar physics except through gravity or faint quantum connections. In this view, the visible universe humans inhabit might represent only one small island inside a far larger cosmic structure filled with unseen forms of existence. There are even theories suggesting our universe may not be unique at all. Certain interpretations of quantum mechanics and cosmology imply the possible existence of multiple universes, vast collections of realities emerging from deeper physical laws. In eternal inflation models, space-time may continuously generate new universes endlessly, each potentially possessing different physical constants and structures. Meanwhile, some interpretations of quantum theory propose branching realities where every quantum possibility unfolds across immense networks of parallel outcomes. These ideas remain speculative, yet they reveal something fascinating about the direction modern physics has taken. The deeper humanity investigates existence, the less reality resembles a simple mechanical machine, and the more it resembles an immense hidden landscape far beyond ordinary intuition. And perhaps the most mysterious aspect of all is consciousness itself. Physics can describe atoms inside the brain. It can model electrical activity between neurons. It can analyze chemistry and biological structures. But subjective awareness, the feeling of being conscious, remains profoundly mysterious. Why should arrangements of matter produce inner experience at all? How does the universe become aware of itself through conscious beings? Some scientists argue consciousness will eventually emerge naturally from neuroscience and computation. Others suspect something deeper may be involved, though mainstream physics remains cautious about such ideas. Still, the question lingers quietly beneath everything else. Because if reality already contains hidden layers beyond ordinary matter, beyond visible space-time, perhaps consciousness too belongs to structures humanity does not yet fully understand. Of course, science demands evidence. Speculation alone means little without experiment. This discipline is precisely what gives physics its strength. Ideas survive only if reality confirms them. Countless elegant theories have disappeared because nature refused to cooperate. And this is important to remember while exploring hidden possibilities. The universe does not owe humanity comforting answers. Many current anomalies may eventually dissolve completely under better measurements. Some theories may prove entirely wrong. But even uncertainty itself carries beauty, because uncertainty means reality still contains undiscovered depth. Tonight, somewhere beneath Switzerland and France, proton beams continue circling silently through the tunnels of CERN. Somewhere deep underground, detectors continue waiting patiently for dark matter interactions that may never come. Somewhere across the universe, black holes bend space-time while invisible halos of hidden matter shape galaxies in darkness. And here on one small planet orbiting one ordinary star, conscious beings continue asking questions powerful enough to reach beyond the visible surface of reality itself. Perhaps that endless curiosity is humanity's greatest achievement. Not certainty, not answers, but the willingness to keep descending deeper into mystery. And as we move further into the darkness beneath matter, another possibility slowly emerges from the silence. The possibility that reality may never truly end at all, but instead unfold forever into deeper and deeper hidden layers beyond anything human imagination has yet conceived. If you step outside late enough at night, away from cities and artificial light, there comes a moment when the sky no longer feels distant. The stars stop appearing like scattered points overhead and begin feeling more like openings into something vast and immeasurably deep. Ancient people often described this sensation spiritually, as though the universe were alive with hidden meaning beyond human understanding. Modern physics, surprisingly, has not erased that feeling. In many ways, it has intensified it, because the deeper science descends beneath matter and space-time, the more reality begins resembling an immense hidden structure whose true foundations remain concealed beneath the visible world. And perhaps nowhere is this more haunting than in the realization that ordinary matter itself may be only a temporary arrangement emerging from deeper invisible processes. Everything familiar around you, your body, the earth beneath your feet, the air in your lungs, the stars burning across the galaxy, is constructed from particles that may not even be permanent in the deepest sense. Quantum fields fluctuate endlessly beneath existence. Particles emerge and disappear. Empty space seethes with invisible motion. Matter itself may simply be a stable pattern arising from deeper underlying dynamics, much like a whirlpool forms temporarily within flowing water. This perspective changes the emotional meaning of solidity entirely. The chair beneath you feels fixed and stable because human senses evolved at ordinary scales where quantum uncertainty averages out into predictable behavior. But beneath that apparent stability lies a restless microscopic world filled with probabilities and fluctuations. Atoms are mostly empty space. Electrons do not orbit nuclei like tiny planets in neat circles, but exist as diffuse clouds of probability spread across space. Even the vacuum itself is alive with activity. The solid world humans experience emerges from deeper invisible behavior hidden beneath ordinary perception. And if emergence happens at one layer of reality, physicists naturally wonder whether it continues further downward. Perhaps particles emerge from deeper structures. Perhaps space-time emerges from quantum information. Perhaps even physical law itself evolves from hidden mathematical relationships beyond current understanding. One particularly fascinating possibility involves the idea that the universe may fundamentally operate through information rather than matter alone. Some physicists now suspect that information could be more basic than particles or fields themselves. This idea gains strength partly through black hole research. When matter falls into a black hole, quantum mechanics insists information cannot truly disappear. Yet black holes seemed capable of destroying information completely, creating a contradiction called the black hole information paradox. For decades, this paradox deeply troubled physicists because quantum mechanics depends on information being preserved. Eventually, many researchers concluded that information must somehow remain encoded at black hole boundaries rather than vanishing entirely. This insight helped strengthen the holographic principle we explored earlier, the proposal that space-time and physical reality may emerge from deeper informational structures. In this vision, the universe begins resembling something astonishingly abstract. Reality may not fundamentally consist of things moving through empty space. Instead, existence may arise from relationships, correlations, and information woven together beneath perception. Space becomes emergent geometry. Matter becomes excitation patterns. The universe transforms into something closer to a vast dynamic process than a collection of separate solid objects. And strangely enough, this perspective reconnects modern physics with ancient philosophical ideas from many cultures. For thousands of years, philosophers and mystics suggested that ordinary appearances might conceal deeper, hidden unity beneath the visible world. Of course, ancient spiritual traditions and modern science operate very differently. Physics depends on evidence, measurement, mathematics, and experiment. Yet emotionally, both journeys lead toward a similar intuition that reality possesses hidden depth beyond immediate human perception. Perhaps this explains why so many people feel emotionally moved by discoveries in cosmology and quantum physics even without understanding the equations. The discoveries touch something ancient inside human consciousness, the awareness that existence is far stranger and more mysterious than everyday life suggests. And still, despite all humanity has learned, the greatest mysteries remain unresolved. What happened before the Big Bang? Why do physical constants possess the precise values allowing stars, chemistry, and life to exist? Why does quantum mechanics produce probabilities instead of deterministic certainty? What exactly is consciousness? What is dark matter? What is dark energy? The mysterious phenomenon causing cosmic expansion to accelerate. These are not small gaps in knowledge. Together, they represent enormous missing regions inside humanity's map of reality. The visible universe remains surrounded by vast oceans of uncertainty. Yet there is something strangely peaceful about this. Because mystery means the cosmos remains alive with possibility. Imagine if physics were completely finished. Imagine if every equation were solved and every layer fully understood. In some ways, the universe would become smaller emotionally, reduced to a closed mechanical system with no remaining wonder. But that is not the world humanity inhabits. Instead, modern science reveals a cosmos still overflowing with hidden structures waiting to be discovered. Even now, future revolutions may already be approaching quietly. New generations of particle colliders are being discussed, machines vastly more powerful than the Large Hadron Collider. Future observatories may map dark matter directly through gravitational effects. Quantum computers could eventually simulate physical systems currently impossible to calculate. Perhaps entirely new branches of physics remain undiscovered simply because humanity lacks the conceptual tools to recognize them yet. History suggests caution whenever people assume understanding is complete. Before radio waves were discovered, humanity had no idea invisible signals continuously filled space. Before bacteria, people did not realize microscopic life surrounded them constantly. Before quantum mechanics, nobody imagined empty space itself fluctuated with hidden activity. Reality repeatedly turns out to contain layers human beings never suspected beforehand. So perhaps another hidden layer already surrounds us now. not metaphorically, literally, invisible structures flowing through space-time, unknown particles drifting through galaxies, hidden dimensions curled beyond perception, deeper laws quietly generating the physical universe humans experience every day without noticing. And maybe one day, centuries from now, future civilizations will look back at today's physics the way modern humans look back at ancient atomism, impressed by how close humanity came while still remaining only near the beginning. Tonight, though, beneath the silent stars, perhaps it is enough simply to appreciate how extraordinary the mystery already is. That conscious beings composed of temporary arrangements of quantum fields learned to question the nature of reality itself. That tiny creatures on one small world became capable of glimpsing the hidden architecture of the cosmos. And somewhere out there, beneath matter, beneath space-time, beneath even the deepest equations humanity currently understands, the universe continues waiting quietly, layer after layer unfolding endlessly into the dark. As humanity continues searching for hidden layers beneath reality, one truth becomes increasingly difficult to ignore. Every major scientific breakthrough has revealed that the universe is not arranged around human intuition. The Earth was not the center of creation. Time was not absolute. Matter was not solid. Empty space was not empty. Again and again, reality has turned out stranger, deeper, and more abstract than the human mind naturally expects. And perhaps the next discovery waiting beneath the standard model will challenge human understanding even more profoundly than everything that came before. Because at the edge of modern physics, the distinction between something and nothing has already begun to blur. Consider the quantum vacuum itself. In ordinary language, vacuum means emptiness, complete absence. Yet modern physics describes empty space as an ocean of fluctuating fields filled with hidden activity. Virtual particles emerge and vanish continuously. Quantum fluctuations ripple beneath existence. Forces arise from invisible interactions occurring even in perfect darkness. In some sense, the vacuum is not emptiness at all, but a kind of restless foundation from which reality itself emerges. This becomes especially important when discussing the birth of the universe. For centuries, people assumed creation required something external, some force or event initiating existence from outside reality itself. But quantum cosmology introduces stranger possibilities. Certain models suggest universes might emerge naturally from quantum fluctuations under the right conditions. Tiny fluctuations in primordial fields during cosmic inflation may have expanded into the enormous structures forming galaxies today. In this view, the cosmos itself may have emerged from deeper quantum processes woven into the fabric of existence. And this raises one of the most unsettling philosophical questions modern science has ever approached. Why is there something rather than nothing? Physics can describe how particles behave. It can model cosmic evolution after the Big Bang. It can explain the formation of stars, atoms, planets, and galaxies. But the existence of reality itself, the fact that anything exists at all instead of absolute nothingness remains profoundly mysterious. Some physicists suspect this question may ultimately require entirely new conceptual frameworks beyond current science. Others believe future theories of quantum gravity may eventually provide answers. For now, the mystery remains open, vast, and silent beneath all known physics. Meanwhile, experiments continue pushing deeper. The next decades may become one of the most important periods in the history of fundamental science. Upgrades to CERN's collider systems will dramatically increase precision and collision rates. New neutrino observatories are being constructed to study some of the strangest particles in the universe. Massive telescopes such as the Vera Rubin Observatory and future space observatories will map dark matter across cosmic scales with unprecedented detail. Gravitational wave astronomy, still in its infancy, may eventually reveal hidden phenomena from black hole mergers, neutron stars, and perhaps even echoes from the earliest moments after the Big Bang itself. Each new instrument acts like another sense organ for humanity. Telescopes extended vision. Microscopes revealed invisible life. Particle colliders allow civilization to peer inward beneath matter itself. And with every new technological leap, reality becomes both clearer and more mysterious simultaneously. One reason this process feels almost dreamlike is because human intuition evolved only for survival at ordinary scales. The brain understands falling stones, flowing water, moving animals, sunlight, and seasons. It was never designed to intuit quantum superposition or curved spacetime. Yet through mathematics and experiment, humanity discovered methods for reaching far beyond instinct. Science became a way for consciousness to exceed its biological limitations. Still, even mathematics may not represent the deepest layer. Some philosophers and physicists now wonder whether mathematics itself is discovered or invented. Does the universe obey mathematics because reality fundamentally is mathematical? Or does mathematics merely approximate patterns generated by something even deeper beyond formal description? These questions drift toward the edge where science, philosophy, and metaphysics begin blending together uneasily. And perhaps that blending is unavoidable, because eventually every journey into hidden reality confronts the same profound mystery. The observer is part of the universe being observed. Human consciousness emerged from the very cosmos it seeks to understand. The atoms inside the brain were forged inside ancient stars. The quantum fields physicists study also compose the scientists themselves. In a very real sense, the universe has become capable of reflecting upon its own existence through conscious life. There is something deeply beautiful about that. Across billions of years, matter organized itself into galaxies, stars, planets, chemistry, biology, awareness, and finally curiosity. The cosmos evolved beings capable of asking where the cosmos came from. And now those beings stand at the threshold of another possible revolution in understanding, listening carefully for faint whispers suggesting that beneath everything currently known, deeper structures remain hidden still. Perhaps future discoveries will reveal elegant unifying principles explaining dark matter, gravity, and quantum mechanics together. Perhaps hidden dimensions will eventually be confirmed. Perhaps space-time itself will dissolve into quantum information. Or perhaps reality will prove even stranger than any theory humanity has yet imagined. History strongly suggests the final option should never be underestimated. Before relativity, nobody imagined time itself could slow down. Before quantum mechanics, nobody imagined particles could exist in probabilistic states. Before modern cosmology, nobody imagined galaxies beyond the Milky Way. Reality repeatedly exceeds expectation. And maybe that endless surprise is not accidental. Perhaps the universe is not structured like a finished book waiting to be fully read, but more like an infinite ocean whose deeper regions always remain beyond the horizon. Every discovery expands awareness while simultaneously revealing larger unknowns surrounding it. Tonight, somewhere beyond visible light, dark matter continues shaping galaxies silently. Somewhere inside quantum fields, invisible fluctuations tremble beneath matter. Somewhere near black holes, space-time twists toward conditions current physics cannot fully explain. And beneath all of it may exist another hidden layer still untouched by human understanding. Yet perhaps the most comforting part of this mystery is that humanity does not face it alone. Every person who has ever looked at the stars and felt wonder participates in this ancient search. Across civilizations and centuries, human beings have always sensed that reality contains deeper meaning beyond appearances. Modern science has not erased that intuition. In many ways, it has confirmed it. The universe truly is deeper than it appears. And as the night grows quieter around you now, imagine the hidden architecture flowing invisibly beneath existence itself. Quantum fields humming softly through empty space, unseen matter surrounding galaxies, space-time bending gently around stars, and somewhere below even those structures, another layer still waiting patiently in silence, far beneath the visible world humanity calls reality. And perhaps, after all the equations and particle collisions and cosmic mysteries, the most extraordinary realization is not that the universe contains hidden layers, but that human beings are able to sense their existence at all. Somewhere in the immense history of the cosmos, matter awakened into awareness. Stars forged atoms. Atoms formed worlds. Worlds produced life. And eventually, life began asking questions powerful enough to reach beyond the visible surface of reality itself. That journey, more than any individual discovery, may be the true miracle hidden inside modern physics. Tonight we followed humanity's descent beneath matter, from atoms into nuclei, from nuclei into quarks, from quarks into quantum fields trembling invisibly beneath existence. We explored the Higgs field quietly giving mass to particles across the universe. We followed strange anomalies inside CERN experiments, tiny whispers suggesting that the standard model may not be complete after all. We drifted through dark matter halos surrounding galaxies like invisible skeletons shaping cosmic structure. We approached black holes where space-time itself begins unraveling mathematically. And at every stage, reality became stranger the deeper we looked. Yet despite all this complexity, one pattern remained constant. Every time humanity believed it had reached the final layer, another hidden depth appeared underneath. This pattern has repeated for centuries. Ancient philosophers imagined indivisible atoms. Later generations discovered atoms contained internal structure. Protons and neutrons seemed fundamental until quarks emerged beneath them. Empty space once appeared truly empty until quantum fluctuations revealed invisible oceans of activity hidden within the vacuum itself. Even space-time, once treated as a stable stage upon which physics unfolds, may eventually prove emergent from deeper informational processes beneath reality. And perhaps the reason this endless descent feels both unsettling and beautiful is because it mirrors something fundamental about existence itself. The universe does not appear constructed as a simple machine with one final obvious answer waiting at the bottom. Instead, reality behaves more like an infinite landscape of unfolding depth, where every solved mystery opens pathways toward deeper unknowns beyond it. Some people find this uncertainty uncomfortable. Human minds naturally crave closure, certainty, foundations solid enough to stand upon forever. But the cosmos may not offer such final resting places. Instead, it offers something stranger and perhaps more meaningful, an endless invitation to continue exploring. Because mystery is not failure. Mystery is evidence that reality still contains undiscovered beauty. Even now, somewhere inside the data flowing from CERN's detectors, tiny irregularities may already hint toward future revolutions in understanding. Somewhere inside dark matter observatories buried beneath mountains, the first faint interaction with hidden particles may eventually appear. Somewhere inside future equations not yet imagined, gravity and quantum mechanics may finally merge into a deeper description of existence. The next layer may already be close, waiting silently at the edge of human perception. And if history teaches anything, it is that the next discovery will likely feel impossible beforehand. No ancient civilization could have imagined quantum fields filling empty space. Scientists before Einstein could not imagine time slowing down near gravity. Physicists before modern cosmology could not imagine billions of galaxies scattered across expanding spacetime. Again and again, the universe exceeded expectation. So perhaps the hidden layer beneath matter will exceed imagination too. Perhaps reality is woven from structures stranger than dimensions or particles. Perhaps consciousness itself connects to deeper principles not yet understood. Perhaps spacetime is only a temporary appearance generated from something vastly more abstract beneath it. Or perhaps the universe contains forms of existence humanity currently lacks the concepts to recognize entirely. For now, nobody truly knows, and that uncertainty gives the cosmos its haunting beauty. Because somewhere beyond today's understanding, beyond the standard model, beyond the visible architecture of galaxies and quantum fields, the universe remains unfinished in the human mind. There are still hidden doors unopened, still questions unanswered, still darkness beneath the map. Yet tonight, as the world around you grows quieter and the stars continue their silent movement across the sky, there is something peaceful in realizing that mystery does not diminish reality. It deepens it. The atoms inside your body were forged in ancient stars billions of years ago. The quantum fields moving through empty space also flow through you. The gravity shaping galaxies stretches invisibly across your existence as well. Human beings are not separate from the cosmos observing it from outside. We are part of the same unfolding structure trying, for a brief moment in cosmic history, to understand itself. And maybe that is enough. Maybe the purpose of these journeys into hidden reality is not simply to reach final answers, but to experience wonder more deeply, to feel the immense scale and mystery surrounding existence, to recognize that beneath ordinary life lies an invisible universe far stranger and more beautiful than human senses ever evolved to perceive. So tonight, as you slowly drift towards sleep, imagine the hidden architecture of the cosmos continuing quietly around you, invisible quantum fields trembling beneath matter, dark matter surrounding galaxies in silence, black holes bending space-time in distant darkness, tiny particles racing endlessly through underground tunnels at CERN while humanity listens carefully for whispers from beneath reality itself. And somewhere, far below every known layer, beyond atoms, beyond quarks, beyond space-time and light, the universe may still be unfolding into deeper mysteries no human mind has yet imagined. Until next time, this has been Valoran Sleepy Space Mysteries. Rest beneath the stars and let the cosmos dream around you.